Hello, we're Team 19034, the next-gen turbogenerator lightweight gearbox for Honeywell, and this is our design day presentation. So you can see our table of contents moving from our problem description all the way through concepts, results, and our lessons learned. If you want to look more on these, please pause the video.
So the project was to create a unique lightweight gearbox that will be used in VTOL applications. It is unique in that it has to meet the following requirements. It has to be below 50 pounds and occupy a small space. It has to function within a thermal requirement of 300 degrees Fahrenheit. The system has to take a 32,000 RPM input from the turbine and reduce it to a 21,000 RPM output to 2 generators on either side. And it has to have a sprag clutch integration feature that goes with the unique design of the gearbox.
The objectives for our project are broken down into 3 phases. Phase 1 is the design phase, where we go through different iterations of our gearbox and the different gear combinations that can be used, and selecting a final design to move forward with to Phase 2. Phase 2 is our more in-depth analysis phase, where we do hand calculations for the gears to get the more optimized gear format, do more ANSYS testing to see the more in-depth stress analysis, and making the final design changes and moving on to Phase 3, which is our final ANSYS testing, ordering our parts, assembling the prototype, and testing that prototype.
So now we'll discuss about how we approach the problem. And this was initially done in phase 1, where we performed a trade-off analysis for the different design concepts, which consisted of the different gear types. And through research, and we gained knowledge for each of the concepts, and criteria was established to determine future potential concepts. And initially we started with 9 design concepts, and this was reduced down. So from the initial 9 design concepts, we reduced down to 3 potential design concepts, which we selected to move forward with. And for each of these concepts, we created models, with the major focus being on the weight reduction and also on the total space occupied, as well as research was done for the different materials that we could use for each of the components. So that way we could ensure that we obtained the correct strength and durability that we wanted.
So in phase 2, we finally narrowed our design down to the bevel gear setup. We were able to use AGMA resources to get a preliminary design for the gears, and we were able to use those in the future iterations to redesign and improve the model. We can also see on the right here that we have ANSYS testing done on the first iteration of the design. And the first impressions were that it was a pretty strong gearbox, but the walls around the outsides were a little areas of concern, and we needed to look at how to improve the structure of those. In phase 3, we were able to consult with experts through Honeywell and verify our AGMA calculations to get towards the final iteration of our design depicted on the right. We were able to send the parts out to vendors for production after that, and we were able to get everything assembled for testing. The verification and data is going to follow shortly.
The system requirements stem from the project statement, and our system has broken to 2 subsystems, which are housing gear subsystems. The housing contains mount system, case, cover, gasket, and the gear subsystem contains sprag, input gear, output gear, and shaft system.
Here you can also see going into the phase 1 designs, talking about the 9 designs. We had things from cycloidal to helical to belts and chains. We finally were able to get to a bevel gear design that we were happy with, and you can see the evolution of how we got there below, starting with something very rudimentary and taking the lessons that we learned to limit the space and the weight until we finally got to our final design, which is pictured in the bottom corner. We also here have our requirements verification table. The table was made in order to test the major systems that needed to be tested, analyzed, and inspected. All the model-based information, as well as the weight, were analyzed in SolidWorks. ANSYS was used for stress, strain, and heat tests, and a physical ATP was run to finalize the table. If you look at the table, you can see that almost everything was passed once we were able to do all these different tests, and we were able to verify things according to how we wanted to through the objectives and the requirements of the project.
Results of this project begin with the ANSYS testing, which about the gearbox, and the gears were able to withstand the force with the gear reduction from 32,000 to 21,000, as well as temperature constraints. The ATP was completed successfully, and show that the prototype gears were able to maintain the production standards that were outlined in the AT. And finally, our prototype is ready to be delivered to our sponsor. This is a depiction of the generator gears that were additively manufactured. Next, we have the turbine. And these are the gears in their appropriate meshing orientations. This is the cover that was additively manufactured. Here's the casing depict as well. And these shafts were also manufactured, and they include the key lock inserts shown in black.
The deliverables to sponsors are 3D printed gearbox access testing results, model files, model drawings, model testing results.
In order to demonstrate our products, we used our ATP. You can see here pictured the motor, which was a variable input motor that we use, as well as the test rig that the team designed in order to test everything. The main thing that we were testing for was the gear ratio. You can see in the data sheet here, we were able to get a good gear ratio of 1.57, and all of the tests that we did of 9 total were within 0.04 of our intended gear ratio, leading to the test being ultimately a pass.
The lessons learned during our project over the year is accountability for action items is important. We had consistent results when we executed accordingly to structured action items. Structured and disciplined communications with stakeholders is essential for project success, and it is critical to mitigate changes of requirements and scope creep outside of the initial stages of the project development.
So over the course of the project, we were able to identify and address some concerns that came up with our design. As for safety concerns, the main thing would be debris or deformation that could occur while the gearbox is running. The main thing would be teeth chipping off of the gear. If they were to chip off and then get caught in the gear system, that could somehow affect performance. However, we were not able to verify this as a hard fact, so we would need to do further research into that in the future. Environmental concerns include the inertial and thermal conditions of the gearbox. This would relate to how many G's forward, how many G's down are being applied to the gearbox, as well as the actual operating temperature. We were able to verify that the gearbox functions under those requirements using ANSYS. The lifecycle concerns were addressed using AGMA documentation. These documents account for fatigue by using SN curves, and we were able to design our gears around those limitations to get our lifecycle concerns addressed. And then for manufacturability, the main concern is the unique shaft angle, which will contribute to tolerancing difficulties.
At the end, we thank and acknowledge the support of Jeff Gaimon, the sponsor, Joe, co-sponsor, Mark Brazel, the mentor, our peers, and the greater Honeywell community. We've used AGMA specification documents as references to create and design the gears.